Stage is yours.
Thank you. It's a great pleasure to be here and seeing people in 3D. It's weird. So thank you all for having me. So I'm going to give a kind of slightly out there talk because I got to listen to some of the questions in the panel earlier, and they felt kind of out there and interesting in that way. So I'm not going to show you very much concrete stuff. I'll show you a little bit of concrete stuff to just convince you that I'm not completely making this up. But we're really going to think about the question of how we build generally intelligent robots, right? That's our job. We're AI researchers, we're roboticists. And one of the things that AI researchers in general don't often acknowledge is that AI is a robot problem, right? You and I are robots, we're not computers. And all natural intelligences are also robots. They're not computers. There aren't any, if a brain is a computer, there aren't any brains floating out there in the world that aren't locked into bodies. Okay, so the AI question is a robotics question. And what we really want to be able to do is we want to build these general purpose robots. We want to build robots that are roughly as capable as you and I are, that go out into the world, that solve all the problems that you and I can solve. And that's probably the only well-formed version of the general intelligence question. Okay. So we're going to think about how we can make that real. And what I'm going to talk about mostly is models. And by models, I mean like when you're doing reinforcement learning, you model the problem as an MDP, like a formalism like that, because that's kind of the language that we use when you talk about generalizing across problems. But it's important to bear in mind that models aren't real, right? They're just useful. Only robots are real. Okay. So I'm gonna kind of lay out a sort of a program here for building a generally intelligent robot and ask what that program needs to contain. And I'm going to argue that it has to contain 4 things, one of which is a little loose and not really my area of expertise. So, but I'll talk about the other 3 in more detail. The first one is we need to write down a decision theoretic model of the fundamental process, like how does the robot interact with the world? What does that mean? We have to write down a model for that that's formal that we can do math things with. We have to agree on what that looks like. The second thing is we need to explain how one agent that's like wildly overpowered, and I'll explain what that means in a little bit, can solve any problem, because that's what intelligence means, right? If you're just able to solve one problem well, you're a dishwasher or a dung beetle or some sort of interesting appliance, but not really an intelligence. And then we'll talk about and that first problem, that one agent can solve any problem, will sort of unify hierarchical reinforcement learning and AI. The second one, a plausible explanation for innate, what should be built in versus learned. We'll talk about how robotics fits into this kind of abstract model that we're talking about. We'll make it more concrete there. And then finally, we'll talk a little bit about language and inter-agent communication more generally, how that fits in. Okay, so let's talk first about the decision theoretic model of the fundamental process. Okay, and this seems fairly obvious to me, but it's not obvious to everyone, so I'll talk through it. You have the world, okay, not a problem, but the world, which is different to a problem. And then you have a robot that can take actions in the world, and it's going to get back some sensory signal at every time step. And then what we're going to do is we're going to model it, and that sensory signal is inexorably partially observable, right? There's just no way around that. It's just, it's a big world, small robot. It's inexorably partially observable. And what we're going to do is we're going to hand it tasks. Okay, this is what it means to be general purpose, right? There's many tasks that we can give the robot, and for now, we're going to say that every task is described roughly by a reward function. Okay, how you describe that reward function is a complicated question. What it comes with, for example, if you describe it in language, it comes with a lot of stuff. It's not just someone following around a robot with a yes/no button saying you did the right thing or you did the wrong thing. It can be like arbitrarily complicated. Okay, but that's drawn from some distribution over tasks. So this is a kind of a multitask POMDP. Okay, it's a partially observable Markov decision process. You get observations. They're not sufficient to tell you about your task or your reward function, but you have a fixed set of actions and observations because you're one robot. Okay, that's fixed. So we call this the ego process. Okay, so the robot just has that process. That's how it interacts with the world, and that's kind of that. And where the structure of things get interesting is what the hardware of that robot does is it induces a POMDP. Okay, so if you change the hardware of the robot, it changes the attributes of the POMDP. So if we want to talk about the relationship between the formal model and the real thing is a machine that induces an appropriate formal model that we can work with. You can imagine searching over robot bodies by thinking about the POMDP they induce and how hard it is to solve a distribution of tasks you might care about. Okay, and so, in principle, we could just do deep reinforcement learning plus like some memory thing and be done. In principle, that works. In the limit of data with a powerful enough function approximator and gradient descent, it solves the problem. Okay, so let's talk about why that might not scale. And that's because we need to explain how one agent can solve any problem. How one agent with a wildly overpowered state and action space can solve any problem. When you're in AI and you're attacking a single specific problem, like Go, or deciding whether or not X-rays have evidence of disease, or you're trying to answer a question, what you start out with is you start out with a well-framed problem. Someone says the input space is the space of all Go boards, and the output space or the action space that you can take is the space of all legal Go moves, and then here's an objective function. And they sort of assume that that comes with a problem, right? Like it appears, it kind of gets instantiated that way, sort of drops from the kind of universe into your lap as a well-formulated MDP or POMDP or something like that. But if you have a general purpose and intelligent embodied agent, that's not how you get to solve those problems. You have to solve all of them in the sensorimotor space of the robot. Okay, so we call this the sensorimotor dilemma. As you get a more interesting agent that can solve more tasks, the less well-suited its input and output space is to any of those individual tasks. It's got to be able to do the union of all of them, right? So if you need an agent that can play Go, and that can read, and that can play chess, and that can juggle, and that can, make a movie or build a building, in addition to all those things, it's got to have a really overpowered sensorimotor space, like definitionally. And so resolving this dilemma, I think, is the most interesting question in scaling robot learning. The more general purpose you are, the less well-suited your sensorimotor space is to any of the problems you might want to solve. We have to overcome that. So, for example, if you want to learn to play chess, we can drop in alpha beta pruning into a chessboard if you define the state space in the right way. It performs as well as the average club chess player, and we're done. Okay, but that's not what a robot gets. A robot gets a much richer image of that chessboard, very, very rich, high definition, and all of those chessboards, by the way, represent the same position. So there has to be an abstraction under which the robot takes those chessboards, converts them into an abstract thing that talks about what's important to chess, not what's about the robot's sensory motor space. Okay, so the right way to play chess is to think about an 8x8 board, six types of pieces, 2 colors, and your legal action should be chess moves. You don't want to think about whether you have a HD camera or a 4K camera running at 60 hertz or 30 hertz, whether you've got a 6-degree of freedom arm or a 4-degree of freedom arm. That's about the robot. When we're trying to solve a problem, we shouldn't care about the robot. We should care about the innate complexity of the problem. Okay, so bridging this gap is this sort of interesting question. And what we've been working on for a long time in my lab is a way of doing this. Okay, so I'm going to talk about MDPs for now just because it's easier, but the same sort of thing applies to a POMDP. If you start out with the ego process, like a really high dimensional state and action space, and then you give the agent a reward function, and you don't want to solve the problem in that MDP is crazy. Okay, it's just wildly overkill. What you would like to do is instead solve the problem in a much more abstract MDP. Abstract states, chessboards, abstract actions, legal chess moves, reward function that expresses what happens when you play those legal chess moves. All you need to do is you need to abstract out the robot's state, that's its perception. So instead of perceiving an HD thing, you need to perceive a chessboard, and you need to abstract out its actions. Instead of moving its motors a little bit, you need high-level manipulation skill of the kind that several of the speakers have been talking about, like moving a piece. And if you can build those two things, you're in a whole new MDP. If you build those two things right and they happen to be compatible with each other, then you can get into the MDP that describes the complexity of the problem, not the robot. Okay, and it turns out that if you start with a POMDP, you can get to any other decision-making formalism by just special casing it. Okay, so for example, if the states and the actions are discrete, you've got a good transition function, and your reward function is goal-based. Once you know that, you can just do search. You can just do alpha. You can just do A star. Okay. If the transition function looks adversarial to you, then maybe you need to do adversarial search. If your states are factored and your actions are factored and they're both discrete and you've got a good transition function, then you're in classical planning. Okay. And if your states are high dimensional and continuous and your actions are discrete and your episode terminates after every action, then you're in a contextual bandit. And if you have demonstration data for that contextual bandit, you're in a supervised learning algorithm. Okay, you can get to all of them. Like every chapter in Russell and Norvig is like a specialization of a POMDP. So it's POMDP with extra structure in it. Okay, so you can imagine that what we're going to go do is we're going to build a robot, we're going to hand it a reward function per task, and it's going to go build a representation of the world as a complex MDP or POMDP that matches the complexity of that task, of that problem. And then it's going to exploit the structure in it by pulling in an off-the-shelf algorithm that says, hey, this is discrete and factored, and the transition function looks adversarial. I'm going to pull in alpha beta pruning, and I'm going to play chess just as well as a club chess player, 0 shot. Okay, if we're trying to navigate around in the world, we build a map of the world and it looks like a graph and it looks deterministic to us. The right data structure looks like a map and we do a star and we navigate through that thing. And maybe it's the case that we're trying to play soccer and the state and the action space are just continuous and real valued and there's no way to get around that and we can't get a good model and now you need to do policy search. That's fine. Key thing is you want to match the representation to match the problem, the actual innate complexity and structure in the problem, and then you want to swap in an off-the-shelf algorithm to do that. Now, there's a lot of complexity here. Okay, so one question is, when do you know that this thing is discrete? When do you know that it's continuous? When do you know that it's factored? How do you know that your model's good enough? A lot of questions. I'm just going to show you one tiny piece of work just to say that this is a thing that it's not impossible to imagine doing. Okay, so this is from a 2018 JERA paper. On the left there, you'll see an image of a room which has got a cupboard and a cooler and a switch in it. There's the cupboard, there's the cooler, there's the switch. And I just went to, so I'm just going to do one half of this problem. I'm going to handwrite the procedural abstractions, the motor skills, and we're going to learn the state abstractions, the symbolic representations from this. So some rules here. I wrote skills to go between these two, the cooler and the cupboard. I wrote a skill to open and close the cooler and open and close the cupboard. I wrote a skill to switch the switch on or off. And then there's an object that's sometimes in the cupboard or the cooler. If you can view it, I wrote a skill to pick it up and put it down. A couple of catches. If you're standing in front of the cupboard and you open the door, you can't get to the switch. It's physically blocked. Also, when the switch is on, there's a really bright halogen light in there. I got the brightest one I could find. It wipes out the thing that you use to detect what's inside the cupboard. It just looks white. So you can't manipulate stuff in the cupboard if the switch is on. And then the robot, when it holds this object, you can kind of see it, it's kind of holding it up there. And it can't open and close the cooler of the cupboard when it's holding an object. It needs both hands. Okay. So you can imagine writing down a small description of that problem and it would be tiny, right? You'd say, well, the object's, you're holding the object or you're not, or the door's open or closed or it's not. But that's kind of cheating, right? We want the robot to start out with perceptual data like this. And actually, more formally, what we start the robot out with, we start it with its pose in the map, X, Y, theta. We start it with a voxel grid of the entire room. I'm just showing you one part clipped here. And we start it with its raw joint values. And then we send it out in the world and we ask it to execute some of these motor skills. So it executes 160 motor skills total, takes about an hour and a bit. See that it's opening and closing the cooler. And then it's picking the object up and putting it down. It's turning the switch, which you can do with one hand, but it's got to go put the object up in order to open and close the cupboard. There you can see there's the light on, very bright. Okay. And from that data, 160 executions, we can learn a symbolic representation using algorithms developed in my lab. Okay, so what you get out is you get out this piece of text. This says if you want to navigate to the cooler, the precondition is that symbol 1 should be true. Afterwards, symbol 0 will be true and symbol 1 will not be true, and it'll take about 37 seconds. So just to show you what those mean, they're distributions over the robot's low-level state. That's what the symbols ground to. They're learned distributions. The robot's identified which distributions it should model. It's modeled them, and it's built a representation out of them. So if we draw samples from those distributions, symbol 1 is a distribution of the robot's location in the map. So I drew some samples and drew it. You see it's kind of pointing up there. That's where the cupboard is. And then symbol 0 is a distribution of its location in the map. It's standing over there looking right. That's where the cooler is. Okay, so this says if you're standing in front of the cupboard, you can execute and move to the cooler. You won't be standing in front of the cupboard anymore. Now you'll be standing in front of the cooler. Okay, but that's using learned grounded symbols. Here's a more interesting one. If you want to open the cupboard, you need to be standing in front of it. We've done that one already. Symbol 3 needs to be true. That's a distribution of the robot's joints. You'll notice that the hands are down here. So it's not carrying an object. It's not got anything in its hands. Symbol 4 is a distribution over the whole voxel grid of the room, but I've just clipped out the interesting part that changes. That's the cupboard. You see that maybe the switch is on or off, but the cupboard is closed. Afterwards, the cupboard won't be closed. It'll be open. Maybe there'll be an object in it. Maybe there won't be. Maybe the switch will be on. Maybe there won't be. Okay. That's what a learned grounded symbolic representation looks like. And you can prove that if you do this thing in the limit, you'll learn a sound and complete symbolic representation, that if there is a plan, this will find it. If there isn't a plan, it won't. Just going to skip some of these in the interest of time. And just to show you what happens when we want to do planning. So here's the robot. I want it to pick up an object inside this cooler. Notice that the light switch is on. And what it does is it takes that PDDL representation, it discards the grounding, it inputs them into a classical planner, which takes 4 milliseconds to find a plan because it's a really easy problem. It opens the cooler, but it doesn't pick up the object because it needs both hands to open the cupboard. Moves to the cupboard, but it doesn't open the cupboard because it knows it needs to turn the switch first before it opens the cupboard. Then it goes back and gets the object and puts it in the cupboard. So that's what a classical planner classically does, right? That's not surprising once you're in that representation. Okay, so the point here is not that we solved the hard planning problem. The point here is that we took an extremely complex problem. We learned the correct representation of that problem, which is not complex, and that was amenable to use in a classical planner. An algorithm that was already exists because people study that for decades. So the slowness here is the vision processing because I'm bad at that. I'm not very good at computer vision. So it takes a little while to do the point cloud merge. But the planning was 4 milliseconds and it builds a complete policy that you can execute from anywhere. And it closes up the door in the cupboard and that sort of stuff because I asked it to. Okay, and you know, just to say that it's not a fluke or a once-off thing, we've applied this in many domains now. I think 6 of them are real robot domains. This one that you can't quite see because it's dark in ICLR is an object-centric lifted one that learns operators in Minecraft from pixel data. And we've got a couple of robot ones in submission at the moment. Okay, so that's all well and good, but everything there was learned completely from scratch with no knowledge of the world and no physics or anything like that. So that's why it took 160 executions to learn something dumb like you need to open a door before you can get the thing inside it, right? And that was cool and fun, but now we should think about all the technology we have in robotics and how we can make this less hard to learn. And now I'm going to conjecture wildly, so you know, feel free to have your eyes glaze over. But at the moment, what we're doing is we're learning one jump. We're learning the abstraction, the state and action abstraction in one go. Well, instead, what we should be doing is we should be learning a hierarchy that builds up. And the reason why we may want to do that is because, you know, we want to start at the ego process, learn a bunch of layers of abstraction, each one of which is a POMDP in the fully general setting, until we do something like playing chess. And then if we want to play checkers, it's a branch off that thing. Okay, so you've reused a large fraction of those learned abstractions. And then if you want to do something like, you know, learn to navigate through the world, you learn a different hierarchy of abstractions. And if you want to learn to play soccer, you learn a different hierarchy of abstractions. And then if you had to learn all these things, what you would find is that a large fraction of the hierarchy would be shared. Okay. And my guess is that it'll be the first couple of layers that you would have to learn every single time you did this. And those layers, you could sort of draw a line and you could say everything below here, you're going to need to base almost all your abstractions on. And those things are going to represent the structure in the world and the robot, not the problem. So like above that line is like problem-specific abstraction learning. You just got to learn it on a per problem basis. But stuff below this line is got to do with like the fact that the world's 3D, or that, you know, most problems can be represented as a collection of objects and stuff like that, right? That sequence of things, we think you should build that in. So we call that, we like giving things fancy names. We call that the sensorimotor substrate. Okay, those are the stuff that should be built in. So if you look at that distribution of the tasks and you look at that robot and you look at the structure of the world and you imagine repeating this over and over again, you could imagine that the first few layers of abstraction, which would be very expensive to learn, would always look the same. And that's what you want to build in. Okay. So what goes in there? Anything that explores structure in the world, not a specific task, any structure in the ego process, any structure in the distribution of the tasks. And the key thing is that they're always coupled, perceptual and motor abstractions. Okay, so skills and symbol and abstractions over your perceptions. Okay, and if you think about what we are doing in the field of robotics, largely is we are building those things. We're building abstractions that exploit properties of things in the world. So let's make that a little more explicit. When we do computer vision, well, this is a tiny picture, but that's a picture of a scene, and all the objects in it have been kind of pulled out in, you know, we've done computer vision on it, we've labeled the objects and maybe their attributes. That's a perceptual abstraction. You used to have to take in a huge matrix of pixels. Now you take in a list of objects that are present in the scene. If you think that most problems actually can be solved at an object level instead of a pixel level, then that's an abstraction at the perceptual level that you're going to have to use a lot. There's a lot of abstraction of actions. For example, motion planning is an abstraction of actions. Instead of deciding how to move all of your joints, torques, you decide where you want your hand to be, and motion planning computes your location over there. And now you only have to do actions in where you want your end effector to be. Okay. Similarly, where how you choose to do a grasp, that's an action abstraction. All right. And things like SLAM are actually abstractions over POM-DPs. Okay, so if you take SLAM, that's a POM-DP, and then you add localization, now you're in an MDP. And if you add mapping, now you're in an MDP with a model in which you can do motion planning. That is the compatible action abstraction, fits together with SLAM and removes most of the partial observability of that problem and lets you plan at a much higher level. Where do you want to put your base? Okay, so our conjecture is that the way that we want to kind of put all the different pieces of robotics back into a single coherent structure is to say what robotics does is it builds those things that are common in the world, things like kinematics and dynamics and partial observability, builds layered abstractions that get rid of partial observability and bootstrap problem-specific learning to make it as fast as possible. Okay, the way to scale robot learning is to avoid it, right? So in learning, you want to minimize task, you want to minimize sample complexity. Okay, so how do you minimize sample complexity? You don't learn if you can help it. Okay, very last thing, how am I doing for time? We've got a couple minutes.
5 minutes.
5 minutes, okay, good. The last thing I'm going to talk about very briefly, there are people at Brown who are much better at this than me. I'm going to talk a little bit about language and interagent communication and what the implications are. If you decide that this is your model of how an agent interacts with the world, it starts with an ego process POM-DP, it builds abstract representations. And now what it needs to do is it needs to take language and those need to inform those abstract representations. Okay, so how do we go up to an agent that has a very high dimensional interaction with the world and we say, hey, please pick up a stapler. The key thing is that what you want to do is you want to take that language, you want to ground it into that hierarchy. You want to ground it into formalisms of partially observable Markov decision processes. You don't want to ground it into images. You don't want to ground it into videos. You don't want to ground it into anything except a sequential decision banking model, because that's what you and I are solving because we're robots. Okay. And the trick is, okay, we've got some built-in sensorimotor substrate. Roughly speaking, the stuff underneath here is continuous. A lot of the problem-specific stuff we expect to be discrete. It's much easier to talk about discrete stuff with language. So if someone comes along and says, hey, hand me the stapler, and you've built this whole big tree of all your various abstractions, and they're all POM-DPs or specializations of POM-DPs, you have to decide how you're going to ground the language into all those various things. Here we can take a hint from language. So we can take a hint from the structure of language. So we've had 2 students at Brown who wrote a really nice paper showing that if you look at the parts of speech in language, and if you believe that language grounds to something like a decision-making paradigm, like an MDP or a POM-DP, you find that the grammatical structure of language strongly suggests that you're using a very structured model. Okay, the fact that you use nouns mean that you're in an object-oriented setting. Okay, proper nouns mean individual objects. Common nouns means you have types. The fact that you can say tree and talk about the whole class of trees mean that you're not operating solely on a pixel level. It must be the case that you're identifying trees in the world and you're putting them into a class. Okay, the fact that you use verbs are discrete names for actions you can take, mean that you're using discrete skills somewhere in your decision-making paradigm. The fact that you use adverbs, which modify the execution of a skill, mean that those skills have to have parameters. If you can kick a ball harder or faster or higher, that means it's not just a propositional skill, it's a skill with real valued parameters. The fact that you can make statements like the stapler is in my office, that's a factual statement, means you can't be in an MDP. Because if you're an MDP, you would just observe all the things you need to know every time step. You have to be in a POM-DP. Otherwise, it doesn't make sense to inform someone else of a fact about the world that way. Okay, so actually what language suggests is that we're using very, very structured decision processing, decision-making paradigms somewhere in that tree, right? Maybe the first few levels aren't, but eventually they have to be. Okay, a couple of instances where we've done things like learning symbolic representations and mapping language to them. It's an RSS paper. I guess it was 2 years ago now, somewhere during pandemic time. It's a bit of a blur. Nakul Gopalan, who's now a professor at Arizona State, but was a PhD student with Stephanie Telex at the time, and then was a postdoc at Georgia Tech. Drove this robot around various halls, got trajectories, gave a sentence that described the robot's actions. The trajectories were segmented into skills. Symbols were constructed for planning with those skills, and he learned to map the instructions to sub-goals expressed using those symbols. So you could say, hey, go to the end of the hall, and it would form a little plan to drive the end of the hall using learned symbolic representations. That was a very neat paper. And it combined sequence-to-sequence learning with deep nets, learned symbolic representations, and hierarchical RL. One other thing that's cooking in my lab at the moment, which we don't have, I don't think we have anything public on at the moment, but it's coming out soon. You know, we're thinking about how you do translations of language to decision-making processes like an MDP. And we've seen that there's been a lot of success with neural methods going from sequence to sequence. Okay, so it seems like machine translation is a thing we can do. So what we've done is we've written a domain-specific language for expressing information about MDPs called RLang. Okay, so with RLang, you can write down a short fragment of information about the state or the action space or the transition function or the reward function or the policy or an option or the value function. You can say, whenever there's lava, don't step in it, or always pick up the fruit if you see it, or it's better to be in a state where you're not standing on lava than when you are. You can give sorts of all kinds of hints in whatever format you like. It's a formal language with a formal grammar and a compiler, because we're fancy that way. And the plan is to take natural language and do sequence-to-sequence learning into RLang. And that way you'll be able to, that will kind of get you from the ambiguous complex language to the unambiguous formal precise language of RLang. And then we know how to ground that because it was constructed to be groundable that way. That's kind of to come. Okay, so just to reiterate, to end the talk, I really do think, Georgia is exactly right. We're at like the precipice of being able to do these things, right? It really is the case that we have, an unprecedented opportunity to like actually solve the AI problem. Like all the tools are there, all the compute's there, and the robots are there. Well, the robots are a bit of a pain, but the robots are mostly there. And so I think we should be thinking big about this. We should be thinking about how we make something as generally intelligent as a human, and how we have to structure such a thing. And so these are the 4 questions that I think are the core ones. I don't think there's some argument about the decision theoretic model. Maybe it needs to include extra stuff about time. Maybe we need to be more structured about the reward function. That's arguable. But my sort of core thing is that we need to be able to explain how one agent can solve all the problems. And the best way that we do that is not that we discard the rest of AI, not that we think, oh, you shouldn't have done, search shouldn't have happened. We didn't need that. Everything's just going to be reinforcement learning pixels to motors. No, that should have happened. It's an important subclass of problems. The question is, when does the robot know? How does it frame a task that it's facing into a problem where it can recognize that it's a search problem and swap out an algorithm like that? That's the kind of key thing for me. And this I think is a reasonable account of how we do all this stuff. Okay, that's it for me. Thank you.